Today we're diving into the Thevenin's theorem, a powerful tool in electrical engineering. Have you ever faced a complex circuit and wished there was a simpler way to analyze it? The Thevenin's theorem is your answer. It allows us to replace a complicated network of resistors and sources with a much simpler equivalent circuit. This makes calculations easier and helps us understand how circuits behave. In this video, we'll break down the theorem, explore its applications, and walk through practical examples. Whether you're a student or a professional, mastering the Thevenin's theorem will make circuit analysis much more manageable. Let's get started by understanding what the Thevenin's theorem is all about. Thevenin's theorem states that any linear electrical network with voltage and current sources and resistors can be replaced by an equivalent circuit. This equivalent circuit consists of a single voltage source, called the Thevenin voltage, in series with a single resistor known as the Thevenin resistance. The key is that this simplified circuit behaves exactly the same as the original at the terminals of interest. This means you can analyze the effect of changing loads without recalculating the entire circuit each time. The Thevenin's theorem is especially useful for analyzing power systems and electronic devices, saving both time and effort. Why should we use the Thevenin's theorem? The answer is simple: it streamlines circuit analysis. When working with complex circuits, especially those with multiple components and varying loads, calculations can quickly become overwhelming. The Thevenin's theorem allows us to focus on just the part of the circuit we care about, replacing the rest with a simple equivalent. This is particularly helpful when you need to analyze how different loads affect circuit performance. By simplifying the network, you can quickly determine voltages, currents, and power for any load connected to the terminals. The Thevenin equivalent circuit is a simplified version of the original network. It consists of a single voltage source in series with a single resistor. This combination is connected to the load. The voltage source represents the open circuit voltage at the terminals, while the resistor represents the total resistance seen by the load. By using this equivalent, you can easily analyze how the circuit will respond to different loads. This approach is widely used in both theoretical studies and practical engineering applications, making it a fundamental concept in circuit analysis. Let's talk about the Thevenin voltage. This is the open circuit voltage measured across the terminals where the load connects. To find it, you remove the load resistor and calculate the voltage that appears across the open terminals. This value becomes the voltage source in your Thevenin equivalent circuit. The Thevenin voltage is crucial because it tells you the maximum potential difference available to any load you might connect. Understanding how to determine this voltage is the first step in applying the Thevenin's theorem effectively. Next, let's define the Thevenin resistance. This is the resistance seen by the load when all independent voltage sources are replaced by short circuits and all independent current sources are replaced by open circuits. You calculate this by looking back into the circuit from the open terminals. The Thevenin resistance is important because it determines how much current will flow for a given load. It's a measure of how the rest of the circuit resists current flow, and it's essential for accurate circuit analysis. First step in applying the Thevenin's theorem is to remove the load resistor from the circuit. This allows you to focus on the part of the network that will be replaced by the Thevenin equivalent. By isolating the load, you can more easily calculate the open circuit voltage and the equivalent resistance. This step is crucial because it sets the stage for the rest of the process. Always remember to clearly identify the terminals where the load was connected, as these will be the reference points for your calculations. After removing the load, the next step is to find the Thevenin voltage. This is done by calculating the voltage across the open terminals where the load was connected. Use standard circuit analysis techniques such as node voltage or mesh current methods to determine this value. The result is the open circuit voltage, which will become the voltage source in your Thevenin equivalent circuit. This step is essential for accurately modeling the behavior of the original circuit. Now let's determine the Thevenin resistance. To do this, deactivate all independent sources in the circuit. Replace voltage sources with short circuits and current sources with open circuits. Then calculate the resistance seen from the open terminals. This value is your Thevenin resistance. It's important to follow this process carefully to ensure your equivalent circuit accurately represents the original network. The Thevenin resistance together with the Thevenin voltage forms the complete equivalent circuit. Once you have the Thevenin voltage and resistance, it's time to reconnect the load resistor to the Thevenin equivalent circuit. This new simplified circuit will behave exactly like the original at the terminals of interest. Now you can easily calculate the current through and voltage across the load using basic Ohm's law. This step demonstrates the power of the Thevenin's theorem in making circuit analysis straightforward and efficient. Let's look at a practical example. Imagine a circuit with a voltage source and two resistors in series connected to a load. By applying the Thevenin's theorem, we remove the load, calculate the open circuit voltage, find the equivalent resistance, and then reconnect the load to the simplified circuit. This process makes it much easier to analyze how the load will behave, and you can quickly determine the current and voltage for any value of load resistor. Now let's consider a more complex circuit with multiple sources and resistors. The Thevenin's theorem still applies. By following the same steps, removing the load, finding the open circuit voltage, calculating the Thevenin resistance, and reconnecting the load, you can simplify even the most complicated networks. This method is invaluable for engineers who need to analyze circuits quickly and accurately, regardless of complexity. Thevenin's theorem is widely used in power systems engineering. It helps engineers analyze how different loads affect the performance of generators and transmission lines. By replacing a complex network with its Thevenin equivalent, you can quickly determine the impact of adding or removing loads. This is crucial for designing reliable and efficient power systems, ensuring that voltage and current levels remain within safe limits. Electronics, Thevenin's theorem is essential for designing and analyzing circuits with transistors, amplifiers, and other components. It allows designers to focus on the input and output characteristics of a device, simplifying the rest of the circuit. This makes it easier to optimize performance and troubleshoot problems. Thevenin's theorem is a foundational concept in both analog and digital electronics. Troubleshooting circuits becomes much easier with Thevenin's theorem. By reducing a complex network to a simple equivalent, you can quickly identify faulty components or connections. This approach saves time and reduces the risk of errors. Whether you're working on a small electronic device or a large power system, Thevenin's theorem is a valuable tool for diagnosing and fixing problems efficiently. You may have heard of Norton's theorem, which is closely related to Thevenin's theorem. While Thevenin's theorem uses a voltage source and series resistor, Norton's theorem uses a current source and parallel resistor. Both theorems are mathematically equivalent and can be converted into each other. Understanding both gives you more flexibility in circuit analysis and helps you choose the best approach for any situation. While Thevenin's theorem is powerful, it has some limitations. It only applies to linear circuits, meaning circuits where the parameters do not change with voltage or current. Nonlinear components like diodes and transistors in certain configurations may not be accurately represented by a Thevenin equivalent. It's important to recognize when the theorem can be used and when other analysis methods are required. Thevenin's theorem isn't limited to DC circuits. It can also be applied to AC circuits, where the equivalent voltage and resistance become complex values, including impedance. This allows you to analyze circuits with capacitors and inductors using the same principles. Thevenin's theorem is a versatile tool that adapts to a wide range of electrical engineering problems. AC circuits, Thevenin's theorem uses impedance instead of just resistance. Impedance combines resistance, inductive reactance, and capacitive reactance into a single value. When analyzing AC networks, you calculate the Thevenin impedance in the same way as resistance, but you must include all reactive components. This approach allows for accurate analysis of circuits with capacitors and inductors. Thevenin's theorem is also useful in measurement and instrumentation. When designing sensors or measurement devices, you often need to know how the circuit will behave with different loads. By using the Thevenin equivalent, you can predict the output and ensure accurate readings. This is especially important in sensitive applications where precision is critical. Communication systems often use Thevenin's theorem to match impedances and maximize power transfer. By simplifying complex transmitter and receiver circuits, engineers can ensure that signals are transmitted efficiently and with minimal loss. Thevenin's theorem is a key tool in designing reliable and high-performance communication networks. Control systems often involve complex networks of sensors, actuators, and controllers. Thevenin's theorem helps engineers simplify these networks, making it easier to analyze system behavior and design stable control loops. By focusing on the key components, you can optimize performance and ensure reliable operation. Signal processing circuits often require precise analysis of how signals are affected by different components. Thevenin's theorem allows engineers to model complex filters and amplifiers as simple equivalents, making it easier to predict system behavior. This approach is widely used in audio, video, and data processing applications. Researchers use Thevenin's theorem to develop new circuit designs and test innovative ideas. By simplifying complex networks, they can focus on the effects of specific components or configurations. This makes it easier to experiment and discover new solutions to engineering challenges. Thevenin's theorem is a staple in electrical engineering education. It helps students develop a deeper understanding of circuit behavior and analysis techniques. By practicing with Thevenin equivalents, students gain confidence in tackling complex problems and build a strong foundation for advanced studies. In applying Thevenin's theorem, always double-check your steps. Carefully remove the load, deactivate sources correctly, and use reliable analysis methods. Practice with different circuit configurations to build your skills. Over time, you'll become more efficient and accurate in using Thevenin's theorem for a wide variety of problems. Some common mistakes when using Thevenin's theorem include forgetting to deactivate sources, misidentifying terminals, or incorrectly calculating resistance. Always follow the correct procedure and verify your results. If something doesn't seem right, go back and check each step. With practice, you'll avoid these pitfalls and become proficient in circuit analysis. Modern simulation tools like SPICE make it easy to apply Thevenin's theorem. These programs can automatically calculate Thevenin equivalents for complex circuits, saving time and reducing errors. Learning to use simulation software alongside traditional analysis methods will make you a more versatile and effective engineer. Engineers use Thevenin's theorem in real-world projects to design, test, and optimize circuits. Whether you're working on consumer electronics, industrial systems, or renewable energy, Thevenin's theorem helps ensure that your designs are efficient and reliable. It's a practical tool that bridges the gap between theory and application. Thevenin's theorem is especially useful for analyzing maximum power transfer. By matching the load resistance to the Thevenin resistance, you can ensure that the load receives the maximum possible power from the source. This principle is widely used in audio systems, communication networks, and power distribution. By simplifying circuits and optimizing load conditions, Thevenin's theorem contributes to energy efficiency. engineers can design systems that minimize losses and maximize output, which is especially important in renewable energy and battery-powered devices. Thevenin's theorem is a key tool for building sustainable and efficient technologies. Renewable energy systems, such as solar panels and wind turbines, often use Thevenin's theorem to analyze and optimize power delivery. By modeling the source and load as Thevenin equivalents, engineers can ensure that energy is transferred efficiently, maximizing the performance of green technologies. Circuit designers rely on Thevenin's theorem to simplify analysis and improve design efficiency. By breaking down complex networks into manageable equivalents, they can focus on optimizing key parameters and ensuring that the final product meets performance requirements. Thevenin's theorem is an essential part of the design process. Testing circuits is easier with Thevenin's theorem. By replacing parts of the network with their Thevenin equivalents, engineers can isolate and test specific components or subsystems. This approach streamlines the testing process and helps identify issues more quickly. Maintenance of electrical systems benefits from Thevenin's theorem. By simplifying circuits, technicians can more easily diagnose and repair faults. This reduces downtime and ensures that systems remain operational and safe. Thevenin's theorem is a practical tool for ongoing maintenance and support. In upgrading electrical systems, Thevenin's theorem helps engineers evaluate the impact of new components or configurations. By modeling the existing network as a Thevenin equivalent, it's easier to predict how changes will affect performance and reliability. This ensures that upgrades are successful and meet design goals. Industries ranging from manufacturing to telecommunications use Thevenin's theorem to design and maintain complex electrical systems. Its ability to simplify analysis and improve efficiency makes it a valuable asset in any engineering toolkit. Thevenin's theorem is a standard practice in professional engineering. Innovation in electronics and power systems often starts with a solid understanding of Thevenin's theorem. By mastering this concept, engineers can develop new solutions to complex problems and push the boundaries of technology. Thevenin's theorem is a foundation for creativity and progress in engineering. Collaboration among engineers is enhanced by Thevenin's theorem. By using a common approach to circuit analysis, teams can communicate more effectively and work together to solve challenging problems. Thevenin's theorem provides a shared language for discussing and optimizing circuit designs. Documenting circuit designs is easier with Thevenin's theorem. By representing complex networks as simple equivalents, engineers can create clear and concise documentation. This helps others understand the design and makes future modifications or troubleshooting more straightforward. Many engineering standards and guidelines incorporate Thevenin's theorem as a recommended practice. By following these standards, engineers ensure that their designs are robust, reliable, and compatible with other systems. Thevenin's theorem is a key part of professional engineering practice. Certification exams for electrical engineers often include questions on Thevenin's theorem. Mastering this concept is essential for passing professional exams and advancing your career. By practicing Thevenin's theorem, you'll be well prepared for certification and real-world challenges. Lifelong learning is important in engineering, and Thevenin's theorem is a concept you'll revisit throughout your career. As technology evolves, new applications and challenges will arise. By keeping your skills sharp, you'll be ready to tackle whatever comes next. Sum up, Thevenin's theorem is a fundamental tool for simplifying and analyzing electrical circuits. By replacing complex networks with simple equivalents, you can focus on the parts that matter most and make accurate predictions about circuit behavior. Whether you're a student, engineer, or researcher, mastering Thevenin's theorem will make your work easier and more effective. Congratulations on learning about Thevenin's theorem. You now have the knowledge to simplify and analyze even the most complex circuits. Keep practicing with different examples and explore how Thevenin's theorem applies to your field of interest. As you continue your journey in electrical engineering, remember that mastering fundamental concepts like this will set you up for success in both study and professional practice.